Okay, hello. Quick note before I do anything. There may be some background noise, some banging, some clanking, some sawing. I've got dudes downstairs that are working on installing a water heater for me, so that might happen. Also, I might need to go answer the door real quick or whatever, just in the event that they need me for something. But I think we'll be fine. If I do need to answer the door, I'll throw up the waiting screen again. Okay, it's been a second. Last time we talked, we were clearing up. I'm going to take us over to the website. Last time we talked, we were clearing up relational algebra, and I had done quite a lot of examples. So I hope that gave you a lot of footing on how to do it. Don't forget the book is a good book, actually. There's a reason why I give it to you. It has more information in it than I have necessarily given you. So I'm going to, probably this evening, try to get to looking at your relational algebra homeworks ahead of the other things that I haven't done. I actually thought that I hadn't done the test in here, but it turns out I had, so hey, not quite as bad as I thought. But anyway, that aside, I'll try to get to that homework because I think that is super important to have feedback on before we do test 2 on really relational algebra, SQL, and relational design are going to be what we do there. So today we're going to cover relational design concepts. I'm going to do my best on Wednesday to give you a bit of a example or talk through at least maybe I'll just talk through like the Northwind database or something. But I think that we probably need to talk through the what's and whys of the concepts we talk about today. So that's kind of the map there. Where test 2 ends up is, I'm just going to give it out on. I think it's scheduled for Wednesday. 3/24, yeah, Wednesday, and I think that that's probably fine. I may make it a little shorter if I need to move topics around, but I want to get that done so that we can move on to other things. So today is relational design, which is all about how do you take data that exists and split it apart in the most sensible ways possible and really utilize the abilities of SQL to join and put data together in various ways. So that's what this is about. And it starts with this thing called functional dependencies, which is how you kind of detect where you can split data apart, where you can split a table into 2 tables and not lose any specificity. And then it goes on to this thing called normalization, which is kind of standard ways that we do that. And who knows, I might break some of that stuff up too. I may make this pretty short since there's racket and stuff going on. So I do definitely want to hit really hard the functional dependencies stuff. It's how we get there. There are a couple of things that we get to first, but we'll talk about those. And then after we're done talking about those functional dependencies, we'll look at normal forms. And first, second, and third normal form are the important things that we need to know. We'll look a little bit at general normal forms, but I'm not really going to talk about levels above, I think, third normal form, because it's not normal. And I don't think it's going to help us. So the very end of this, we might skip. Okay. So what are we talking about when we do this? Well, it is good and bad relational database design, right? And we want to write a good schema to represent our data. Now, good can be the enemy of done. So I'm not going to tell you right now. This is a design issue, not a right or wrong issue. I mean, unless you were asked to put something in X normal form, it's not wrong, right? But a design issue about how do you craft your database tables so that you don't have to rejigger them constantly on down the line, right? So we have two kind of levels of this schema. We have what the user sees, which is going to be possibly views, it's going to be the tables that are there, and we have the storage level, which is kind of how we put it onto disk in a way that makes sense. And you defining table schemas is where that comes from, right? So we're really interested in these base relations, because out of the base relation, we can create logical views from queries, and we can use tools like views, which are just stored queries, or stored procedures, which are essentially SQL functions. I didn't really talk about those previously, but we'll talk about them at some point here. So we can craft all those things out of base relations if we get that base relation, that storage level right. And that storage level is all about table schemas, right? So we're going to look at some informal guidelines for what those good schemas are. And really that's all about don't repeat yourself, right? You've probably heard this before, DRY, don't repeat yourself. And it's an important concept in programming in general, but also in database design. So in programming, we say don't repeat yourself. That means organize your code so that you're not like copying and pasting code and you don't have identical code everywhere. Well, in a database, it means about the same thing, except for instead of being code, it's about don't have two fields that have the same value in them in two different places, right? Unless you need to, right? Foreign keys are an example of you need to. So there are some normal forms that define this good database design. And as you go up, we are repeating ourselves less and less and less, right? There are some other normal forms that you can do. We don't need them. 3NF is about good enough, right? If you can master and know third normal form. What the heck happened with that, by the way? I don't think it's supposed to be that way. If you can master and know third normal form, you're going to be all right. I must have been like jamming on the keyboard or something, and the cursor happened to be there when I was editing these. It's been a while. Guidelines. These are the informal guidelines to making a good database design. Number one, we want all of the rows of a table, which they're using the general form of this, each tuple in a relation, but I'm going to say it out loud. The rows of the table should only identify, it should only represent one thing, right? So if you think about having a table of users, right? One row in that table of users should only represent a single user of that system. If you have a row that joins two different user informations together, suddenly you have essentially nonsense in your database, right? And likewise, you don't want to have like users and another concept side by side, because those things may need to be broken apart. So the only thing that you use to represent something that isn't the entity in the table is a foreign key, right? So that is to say, if I have an employee and it's related to a dependent, the foreign key links those two tables together. That's an example of we have something that isn't necessarily part of the user or isn't necessarily part of the dependent, but the rest of it is all just that user or that dependent. So we want to be able to very easily explain our database tables. Now, there's a thing that was kind of pounded into me in one of my grad school programming classes, because my grad school, they used C for pretty much everything in the undergraduate after like the intro classes. So like the intro, I think there were 2 Java classes, and then everything else they expected that you really knew C very well. Regular old C. C89 at that. And I think that's actually very valuable because C becomes very complicated very quickly because it doesn't have a lot of features for code organization. And what was pounded into us was, hey, if you're writing tricky code, that's probably bad code. If you can't easily explain it, that means you don't understand it. And you're not going to understand it tomorrow when you look back at it, and you're going to introduce bugs into your code. The best code out there, oftentimes the most efficient code, to be honest, the best code out there is code that you understand and is clear. Same thing for databases. If it's very, very confusing, that probably means that you have your concepts mixed up somewhere and you could simplify your database some, right? So we want to make sure that the design of our schema is very explainable, right? And if we were to go look at I'm there. I'm finding the page before I show it to you. If we were to go over here and look at the design document for this Northwind database, right? You've probably seen this graphic. Can I get this full image? No, I don't want it that way. I wanted it scaled. How about open image? Eventually I'll get to what I want here. Yeah, there we go. When you look at this database schema for the Northwind, after you read some of the table names and look at how they're coming together, it's honestly pretty easy to see that, oh yes, if I have an order, here's the information, how I get information about that order, and here's the employee that's related to it. If I have an employee, here's how I find what region they're in. Like, you can kind of follow the dots and figure out where the information you might be looking for is. And this is an explainable database. This is actually a pretty good database, to be honest. I mean, they do that on purpose. It is a training database. Okay, so here is the company database. Simplified a little bit, but we have employees. Employees work for departments. So works on gives us the social for the employee and their project number. Projects have department numbers. Departments have managers, right? And we have another table here, department location, that tells us where departments exist. When you look at this schema and you say, well, okay, maybe we want to ask what department how would we ask this? We might ask all of the users, like, first names that a particular project is associated with, right? So we have project here, and we can see, well, okay, I can find projects based on their project name and number, right? And if I follow the dots, I know what department. So if I join project to department, I can get the department that they're involved in. So I can get the department name. I might not even need that, though, because I have D number here. So I can ask, well, who works on that project for that particular department, and join employee to SSN and get their name out. So you can kind of map this thing and see how you're going to end up having to join tables together. One of the most important things in SQL and also in relational algebra is looking to see what shape the data is, what you have to join to get the right data in the right place. And that's what kind of all this normalization is about, is it's about figuring out how to break your data up so that it's joinable and you don't have repetitious information in the database, right? We could just as easily, for example, tack department onto employees. So we have an employee table that also has the department name they work for, the department number they work for, and who their manager is. Right? We could just put these 3 fields at the end of employee, and much of the queries would be very similar still. But it wouldn't be good because we would be repeating department name over and over and over again, right? So what we want to avoid is redundant information. The more redundant information we have, the more likely we are to have problems. We're going to end up with, we're going to end up with these kinds of anomalies, but what these kinds of anomalies really represent is there is information that still exists in an old form and information that now exists in a new form. And if that's the case, we like perform an update or we perform an insert and now the data doesn't match, we may not be able to figure out, in a sane way at least, we may not be able to figure out what the right information is. And then we have a corrupt database, essentially. And if you can't trust your database, you can't trust your project. If you can't trust your project, nobody's going to pay for it, right? Kind of all goes together. And you don't have a job and you're out on the street trying to feed your kids. You don't want any of that. So don't repeat your data, see? Otherwise you'd be on the street. So here's an example. So here we have a relation where we have the employees' projects, and this relation, it's a bad relation, by the way, contains their employee number, what project it is, their name and the project name, and how many hours, right? So now we send an update. We say, hey, that project for P1, it used to be billing, but now it's customer accounting, right? Now, if we do that, and there are 100 employees working on that P1, we've updated 100 records with the same value. All of those users have the same value. If I only update one of them, then I have one with a special value and 100 people that have the same different value. But look, it doesn't make sense because there's only one project and project name that go with, a particular concept, right? So same thing for insert. If I then inserted into that thing and I inserted project P1 with the wrong information, I've got a problem. If I insert and I want to represent an employee that doesn't have a project or a project that doesn't have an employee, I cannot, right? In this table, we have all of these fields, and I can't represent that without an empty value. And we've talked about null before. That would be your option, is to have a null value for whichever side of this you didn't have. And that doesn't make a lot of sense, right? So deletion. When a project is deleted from this relation, it means no employees work on that project. We're deleting all of the employees as well. If an employee was the only person working on a project and we say they don't work on it anymore and we remove that record, now that project no longer exists, right? So these concepts, employee and project, must be separate. They depend on one another because employees do work on particular projects, but they are not the same concept, right? In object-oriented programming, we talk about the idea of is-a versus has-a. And in this case, a project is not an employee, and an employee is not a project. So they should not be in the same table. They're different entities. Now, an employee might have a project, and a project might have employees, but they are not the same concept, right? So we want to keep these is-a, has-a things in mind when we're designing, because if we don't, then we might generate something like this that is busted, right? This will not survive production. So when we do this, what we really want to do is split it apart, right? And what we're looking at, this is the start of functional dependencies. What we're looking at is, what is it that identifies other columns in a table, right? So what we're looking at is a thing called functional dependencies. And what we see here, let's look at A first. We've got that this is employee department, and the key is the employee social security number. Fine, right? Now, if I have a particular employee SSN, that means I know which employee's name it is, what their birth date is, what address they're at, and what department number they are. But this other information, department name and department manager SSN, those aren't really dependent on the user's social security number. Those are really part of whatever department they're in, their department number. So we have two different sets of dependencies. We have one set of functional dependencies that identifies the employee, and we have another set of functional dependencies that identifies the department. Those should be two separate tables. So we would break them apart. Same thing for employee project here. We have the employee social, the project number, and the hours. And with that much information, I can identify how much an employee has worked on a particular project. We also have SSN and employee name. With that much information, I can identify a particular employee. But that's not necessarily having anything to do with hours, right? I can have a name without having hours, right? I hope so. And then another one, we've got project number connecting to the name and location. Well, if hours change, that doesn't mean name and location do, right? And if the employee changes, that doesn't mean the name and the location of the project change. So that is yet another functional dependency. And anytime we find these functional dependencies, these are candidate functional dependencies, by the way, we'll talk about that in a second. We want to break them apart, right? If we can find multiple functional dependencies, that's a sign that there is more than one concept in a particular table. All right. So here's some sample data that kind of drives that idea home. If we look at this data, and I'm going to give us a little zoom here. If we look at this data, notice the redundant information, right? All of the people that work for department number 5 have the same data for DNAME and DManager, right? They're all research in that 33445555. All of the people that work for 4 have the same information as well. So we're repeating ourselves. We need something to identify to link the social to the department, so we can use the department number, the key of the department, to do that. But keeping the name and social in there, that's redundant information. If I split that onto another table, I would only have, given this much data, mind you, we don't have all the data for this table, we're just taking a sample here. But given this much data, I'd have 1, 2, 3 rows in that table. And I wouldn't have any repetitions there because I would have an identifier, so we couldn't have duplicates, right? So the view here, if this were a join between the two tables, would be fine. But as a storage mechanism, if we defined a table with this schema, that would be a bad design of a table. So same thing with employee project down here. We're showing the same issue where we have employee names that are repetitious. Every time Wong Franklin T works for another project, so he works for a couple of different projects here, we're repeating his name, right? And every time somebody works on product X, we're repeating product X through here. Same thing for location. So these redundant fields could be off in their own table and could be joined instead. And then we're storing less information. And we have one source of truth for those bits of information, right? So instead of having whatever, let's just, all of these are samples of data. So let's just pretend for a moment that we have 100 representations of product X in this table versus one representation of product X if we had our own project table where product X only existed as product number 1. project number 1, whatever, right? So that's where this design thing comes, is really to split information and stop repeating ourselves. All right. So the guideline we want here is we want to avoid these anomalies. We want to split data apart where they are present. When we see them, we need to know that they're there. There's some times where you do introduce such things on purpose. It's not like this is a silver bullet. This is a design issue, which means that you, a designer of a table, must have it in mind. This is the reason why I'm doing this thing, and I'm doing it on purpose, right? So as we're designing our tables, we want to avoid having duplicate data, but at the same time, we want to avoid null values. Oftentimes, null values can be stored as separate relations, where if it's null, it just won't exist, right? We just won't have a row for it. And that gets rid of invalid rows of data, right? And just to rewind for nulls, the reason we have nulls is maybe something is not applicable. Again, we can just not store that information in that case. Maybe we don't know it. Sometimes that's okay, and maybe it's unavailable. But if we see a lot of nulls, that's often a sign that we want to split data off into a new table. So, for example, maybe we have an employee healthcare table, right? So one design might be that we have, maybe I should write this down so I don't lose myself in it. So maybe we have one design, I'm going to put a line in the sand here. Maybe we have one design that's like employee, and I'll just say like ID, name, and let's just call it plan title, which is supposed to indicate, maybe you have the high deductible PPO plan for healthcare. Maybe you have no healthcare. Maybe you have a family plan, that kind of thing. Versus, right? So if I didn't know, or I missed open enrollment and I didn't sign up for healthcare, or maybe a family member provides healthcare for me and I don't get healthcare through my employer. There are all kinds of reasons, all kinds of situations that people get in with healthcare that could make that plan title a null field. This also wouldn't be able to support having multiple plans, right? Versus like having employee and plans. So employee is going to be ID still, name, and let's say plan. Actually, let's just leave it at that. Plans is going to have like plan ID and title. And plan will join employee's ID to plan ID. Now, employees can have multiple plans because they can have multiple rows in this plan table. Now, if an employee just doesn't have coverage, they just don't have a row here. We're just not storing information about them instead of storing a null somewhere where it's not applicable or we just don't know yet, right? And as plans get updated, we're not repeating plan names in the employee table. So we can update a single plan name and it'll update for all employees that have that plan, right? So that's really what we're looking at when we're looking at how do I break up data so that I don't repeat myself and so that I can support as little null as possible, right? Again, if you need nulls, that's one thing. They exist for a reason, but as much as we can, it's really good to avoid them. All right. So Another design that we can get ourselves in trouble with is if we end up with bad data for joins, right? So there's a thing called the lossless join property, and it means that the join results are going to be valid for anything that we join together. And essentially what that means is that anytime I do a natural join, which is to say I join with a primary key and a foreign key, the result of that join should only have valid results, and I shouldn't lose information, right? So when I break a table in two, so let's just say, let me go back a little bit. Let's just say we have this situation here with employee department, right? If I break this table in two, and I create a department table out of the department information, and an employee table out of the employee information plus that foreign key, when I join them back together, I should have this data exactly. No rows should be missing, and I shouldn't end up with extra rows. That's the idea behind the lossless join in English. They're going to give us not English here, I believe. And so that's losslessness and non-additive for the join. We preserve those functional dependencies. We preserve the data. And this is very important. Every time we break a table apart, we must make sure that when we join it back together, we get the original information and the relation holds, right? And to be honest, it's the normal way you do this. And the rule there is, well, only put the right fields in the right entity table, right? Okay, so the way we get there is functional dependencies. And I think what I'm going to do here is I'm going to talk about functional dependencies and cut us off. But functional dependencies give us a way to see if our design has turned out well or not. All of those normal forms we talk about will have to do with those functional dependencies. And these functional dependencies are things we find based on the meaning of the data, which means that we must have an intuition about what our tables mean. That means while there would be a right or a wrong answer to how you break it apart, you still have to kind of have a brain about you, and there might be different ways to do it, right? Now, what we say here is that attributes X functionally determine attributes Y. So that is to say, X is an identifier for Y. If I have a value for X, then all the values for Y are unique for that value of X. I think I said that right. We'll see it. Mathematically, right? X given Y holds where any tuples that have the same value of X have the same value for Y. Right? So, again, that means that X has the unique value and Y for every X is the same. This is just our primary key, really. And it goes a little bit further than that because we want to make sure that given a primary key, all of the fields in a table actually depend on it. If a primary key doesn't identify a value in the table, that probably means we could decompose it into multiple tables, right? So all of this comes from real-world constraints. That is to say, you need to understand the problem that you're trying to model. All right. So here's some example. We have social security number in our employee table. Well, there's only going to be one employee named something particular for a social security number because social security numbers don't repeat. Again, that's problematic. Don't use social security numbers for your identifiers because people without social security numbers exist, and if you don't have a social security number in the US, your social security number is some default. I think it's all zeros. But all the same, acting like that's not the case, acting like everybody is a U.S. citizen that has a unique social security number, which means they were born after the Social Security Act and all that stuff. Those are unique numbers for people, right? Same thing for this project. If I have a project number, right, there's only one name and only one place that that project number coincides with. So every time I have the same project number, I should have the same name and location for it. We don't have the project like moving around just because it's a different name, right? Or the last one, given that I know a particular employee and a project I want to know about their effort for, there's only one set of hours associated with that. If there were two sets of hours associated with a social security number and a project, that means somebody was working on a project twice and we've lost information because we have the information in two different places. We've repeated ourselves. So these are a key for hours. So what we're looking at is we want to be able to find these functional dependencies, and when we find them, they must hold for every relation in the instance. So that is, we're going to see examples, and we can say that we think that there's a functional dependency here, but we also must be able to reason out and say, well, that's definitely a functional dependency because of this. That's what this data means, right? All right. Keys always are functional dependencies. They always determine the other data in their tables. By definition, because a key must be unique, that means that it must always be the same value for the other values in the table. Okay. So if we need to know the meaning of attributes and we need to be able to find a functional dependency, that means we need to be able to look at probably a schema and example data to identify these functional dependencies. But importantly, if you have an instance, if you have example data that you're looking at, you cannot say for certain that a functional dependency exists. You can only say that it might exist. Now, why is that? The reason is that, well, just because I see that the data appears to always be unique for that for a particular value, so it looks like for every x, then there's the same y. Example data is just that. There's probably more data out there, or you don't know all the data, or whatever, or there's more data to come later. But we can only say that it might exist. This is a lot like testing. When you test a program, you can only say that for the values that I tested, this program works the way I expected. There are other values that it may not work for. You must prove something in order to do that. So when we're looking at instances, we can say that functional dependencies do not exist. We can find where there are violations of functional dependencies instead, right? So here's an example. Ruling out functional dependencies. So we have a teacher, a course and a text, and we can see where we're going to look for all the pairs of this and say, well, where is there a field that actually does have a unique value for every other value, right? So if we look at text and course, right? Text, given I have Bartram, then I have data structures. Given I have Martin, then I have data management. Given I have Hoffman, I have compiles. Given I have Horowitz, I have data structures. For each unique value in text, I have the same value in course. Just because I have two data structures doesn't mean it broke that. Now, the other direction, right, course to text, that doesn't work. Because I have two values that are the same in course, but they have different values in text. Which means that given course, I cannot identify text. Right? Now we can do the same thing for teacher. Let's say teacher to course. Is that valid? So if I have Smith, then I have data structures. If I have Smith, then I have data management. No. Smith doesn't identify what course it is because Smith has two different courses. We can look for course to teacher. Given I have data structures, I have Smith. But given I have data structures, I have Brown, which means given that course field, I could have two different teacher names, not a functional dependency. Right? And so as we do this, we look at all of the options. Teacher to text also does not work. Text to teacher, I think actually does still work because text is unique through all these four fields. Now, let's talk about that for a second though. So text, given text, I have a unique course. Given text, I have a unique teacher. Or for every unique value of text, I have the same value of teacher and course. That doesn't mean that those are actually functional dependencies. It just means that they might exist. All of the other examples, teacher to course, teacher to text, course to teacher, definitely are not identifiers because they are definitely not functional dependencies. We found where there are duplicates. So what we're looking at is where it may exist. It doesn't necessarily, because there might come another row of this table where it doesn't match. It might be that Bartram wrote the data structures book, but maybe he wrote some other book that somebody else is using for another course, and it breaks all of it, right? So that we can rule out functional dependencies, and we don't need understandable data to do that, right? So here's another example, except for it has general data. It's just a dumb example. And we want to know what functional dependencies might exist in this data, right? So given one field, can I identify everything else? Oh, I should say that, I should go back. Sorry. We could also say teacher and course might identify text because Smith and data structures together is unique. Brown and data structures together is unique. Hull and compilers together is unique. Smith and data management together is unique. So that may be a functional dependency as well. Anyway, back to this. So here we have A, B, C, D, and they have the values of like A1, A2, A3, etc., right? So if I had, let's say, let's just write out the single, we're going to do single attribute key possibilities, right? So the combinations that are possible are going to be A to B, A to C, A to D, B to A, B to C, B to D, C to A, C to B, C to D. I'm actually going to move this to the other side of the screen and do D over here. Sorry. And then D, oh, get the right tool. D to A, D to B, D to C. What we want to find here, given all of these, is which ones might exist. So we have to rule out all the ones that aren't valid. So we'll start with A going to B. Does A identify B? So given A1, I got B1. Given A1, I got B2. That means that given one value of A, I got two different values of B. So A to B does not work, right? A to C. So really, we know that there are three values of A in this example data, so we're really only interested, the way we find these is look for the values of A that have two different, two rows. Are there the same values in the next column that we're comparing it to? So given A1, I can either get C1 or C2, which means A to C does not work. A to D, same story, right? You can either get D1 or D2 for the value A1. So now we do B. And again, we're going to look for duplicate values of B so we can compare them to the other rows. So we have B2 is that. So given B2, I could either get A1 or A2, so B to A does not work. B to C, Given B2, every value of C is C2. Given B1, every value of C is C1. Given B3, every value of C is C4. So B to C might work. It may be a functional dependency. We'd have to know about the data to actually say that it is. So B to D, given B2, we could get either D2 or D3, so B to D is not valid. Right? Then we just keep going. Right? So I'm going to go a little faster now. In C, we have two values for C2, so we can get two different values of A for C2. C to B, C2, C2 are both B2. C1 and C4 are unique, so C to B might be valid. Right? C to D also does not work. And then we can do D. In D, we're kind of interested in D3 because there are two different values of D3 here. So D to A can either be A2 or A3, so no. D to B could either be B2 or B3, so no. And D to C could either be C2 or C4, so no. So the functional dependencies between single attributes is B might identify C, C might identify B. If I wanted to be able to identify all of the rows, right, so we would start with these two. B can identify C. Can it identify everything? It is unique, I guess. No, given B2 and C2, we have a different value for A and D, so no. So we would have to figure out how this data breaks up. All right. I think I'm going to stop here. We're going to talk about the normal forms next time. Like I said, I want to keep the interruptions to a minimum. These functional dependencies, I'll probably have some more examples. These are how we're going to start normal forms. So I might go into this example or maybe another example a little bit next time as well. All right? I'll talk about what my plans are on the test next time. I'm not quite ready on that. Got to make sure that all the right stuff is in the right stuff, but stay tuned for that, and ta-ta for now. Have a lovely afternoon.